La da 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 dum. La da 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 dum. Na 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 na. Okay, students, my wonderful students, let's begin our lecture for today. I want to start with a couple just announcements for the conduct of class and your activities in class. Specifically, if you ever have a problem with the clicker, um, come up here and sit in the front row next to Shy or Darian, and they could help you, fuss with your clicker and get it squared away. Now, we're going to be on frequency BB, all right? And the session is running. If you're getting no bass, then you won't get a check mark. And as always, hold the power button down. If you have a class that uses some other frequency like AA, that's the default setting for iClicker, or BC, I was using BC or CB last spring. If there's other instructors in this building near, like below us or left or right, that are also using iClicker, the frequencies will clash. And if we have differing frequencies, and actually, if somebody's next door and you've got your frequency, you're clicking into their thing, but I won't be getting it. And you'll be getting a check mark for some joker in the psychology department or whoever's teaching next door. Okay, so that's no good. So what you want to do is make sure you're on frequency BB, and I'll try to remind you of that every day because I know some of you have different classes with iClicker. I revised and updated. There's a couple discrepancies in the data from L5 and L6. I updated all that and re-uploaded it. So you may have seen a point or two change, hopefully for the better. But everybody's more accurate now. And this is what the participation rates look like. We've had 6 clicker questions. Last week, remember 2 Thursdays ago, we didn't have class on account of the football game. And so last Monday was actually the first official clicking. Not last Monday, but last Tuesday. Last Thursday, and then this Tuesday. So that's 3 sessions. We've had 6 questions. And 343 out of 582 students have answered all 6. So those guys are in good shape. 100 have answered 5 out of the 6. So they blooped on one of them for whatever reason. And then there's, different participation rates down here. There's 34 of you that aren't on the scoreboard yet. And I know that there's 23 of you that are not registered yet. So you want to make sure you get your iClicker ASAP. Now, you might not be able to get 25 out of 25, but you can still get a good pile of those points if you get your clicker now. But these guys up here, if I was to give grades today, they'd be looking at 25 out of 25. But now, 5 out of 6, that's 83%. So that's below the 85% threshold. So I would have to compute their share of 25, using the 85% threshold. Now I'm going to do some examples of that with you probably in the week after exam 1. We'll have enough points to make it look interesting. This is kind of boring here. But in a couple weeks, after exam 1 is on the books, I'll do an example with you and show you how to handle these guys, the stragglers, which, most of you guys will stay. Most of you are here in the 100% column, and most of you will stay there. And in that case, just 25 out of 25. Ching! But if you blow it, or your roommate accidentally borrows your iClicker and doesn't tell you, and you're down here in the dribs and drabs area later in the semester, in at the end of November, then you're going to have to calculate it. And I'll show you how to calculate that. Okay, questions about any of that stuff? Do you have a question? Okay. I mean, you're not in trouble. I just thought you had a question. All right. How did you guys like that rain on Tuesday? Oh my goodness. We were over Darian and I were over in Harris. And Harris Engineering, the lecture hall, we go out the back door, and it's just a hop, skip, and a jump over to the Physical Sciences building. You cross this little service road that goes behind the Physical Sciences building, and it's maybe from here. Can you raise your hand? No, not you. You. Yeah, don't look at him. Okay, this young lady. Now, what's your first name? Kathy, up here, raise your hand really high. From me to Kathy is how far it was from the back door of Harris Engineering Lecture Hall to the back door of the physics building and safety. But that road, it was like this deep in water. And there was this big drain where the water was, was swirling down like a whirlpool in a monster movie. I was expecting to see the Kraken come up out of there or something like that. It was amazing. And there was, and I heard later, do you remember that sound we heard? That really loud bang, bang, bang. There was so much water going through the sewer that it was pushing a manhole cover up and back down. And you could hear it bang, bang. And it wasn't just once. It was like bang, 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 bang. It's just for like 10, 15 minutes you could hear it. It was astounding. And those manhole covers, that's a lot of kilograms, so you need a lot of force. Well, let's start talking about forces. We were talking about Aristotle and Galileo, and I gave you guys some sketching on the what do you call it? Document cam. Of a Ferrari driving off a cliff, and the mythical frictionless horizontal plane. Let's talk about that. The viewpoint of Aristotle, here's a picture of him from a really old ESPN file. His philosophy was, and I looked it up in an English translation of physics, his physics book. If something is moving, there's got to be something pushing it or pulling it. No matter if it's moving at constant velocity or not. If it's moving, there's going to be a push. Now, that's common sense. That's not bad. He said if there's no force acting on it, if it's at rest, that means there's no forces acting on it. Nobody's pushing or pulling on it. So this Ferrari driving at a constant direction, at a constant speed, 20 meters per second, for instance, he would have said, nope, there's a push force on that. And Galileo's viewpoint was, no, man, not if it's at constant velocity. If that thing is constant velocity, there's nothing, on this frictionless horizontal plane anyways, with a frictionless Ferrari, you don't need a force to keep it going. And that was his insight into motion. And his geometric proof was kind of interesting. We talked about it, and I want to reinforce it this morning. And what we're going to do first is simplify the argument. So we're going to do, we're going to put some numbers in here, but they're all going to be simple numbers. So we're going to talk about a 1 kilogram object like a liter bottle of water. And it's going to be, we're saying it's moving on this frictionless horizontal plane at 1 meter per second. Okay, that's kind of cinchy. And then it also has one generic unit of force. So I'm not even saying metric unit. I'm just saying some generic unit of force, unspecified unit of force, which in the diagrams in the textbook, and oh, by the way, the textbook, apparently Has anybody been able to see my highlighter notes? Raise your hand high if you have. Okay, it's now possible. Great. Um, was it hard? Yeah, I was able to figure it out yesterday. You saw them? Okay, so if you guys were trying to do it and haven't, um, keep your subscription to my Brubeckner at knights.ucf.edu, or type it in again, and my highlights should show up. Now, I don't have any highlights for today's lecture, but I'm going to start doing it. I figured out, they told me what to do on bookshelves so that anybody can view it. So it should be working now. Now, as I mentioned, the diagram in the textbook, the diagram that we used last time, vector W was the weight force acting on it, and that is something that Galileo leveraged to make a discussion and a contra position contra Aristotle, and to hold his position to this day. And so he thought about the downward weight force on something. And so that weight force, it's the force that if you want to hold up that liter bottle of water, you have to exert an upward force of the same size. And in our diagrams, that was capital Y. Okay, and in the textbook, that is vector capital Y. All right. Now, let's get back to Aristotle versus Galileo. So here's what Aristotle would have maintained. That liter bottle of water needs a small push. And we would have forced Aristotle to say, okay, how big of a push? So let's say that Aristotle said 0.100 generic units of force. And for that we use the letter P, lowercase p, a push force, even on the mythical frictionless plane. Now, Galileo was willing to say that you can have constant motion and a little bit of push force, but only under certain conditions. But he said if it's on a frictionless plane, it needs no force. All right, and that's what Galileo's opinion is. And in this specific example, to counter Aristotle's contention, 0.100 generic units of force, and only that, Galileo would say no. Because 0.100 generic units of force is exactly what you get when you're going down a ramp of this shape. He said, I can design a ramp that's the downhill component of the force on a liter bottle of water. All right? And in the diagrams in the textbook, that's the vector labeled D for downhill, down the ramp. Now here's a blow-up of Galileo's ramp. See you, Darian. It's if the weight force is 1 and Aristotle says 0.1, then you make your triangle, your ramp, these proportions. Okay, you take a 1 meter board and you elevate it physically by 10 centimeters, 0.1 meter. And so Galileo said, yeah, Aristotle, any number that you give me, I can build a ramp for which the force that you contend is needed on a flat plane is actually provided by a ramp, and therefore what you're saying is too much. He's saying the horizontal plane doesn't need that much. An inclined plane gives me that much. So horizontal is going to be even smaller than that. And the fact is that there's no minimum number. No matter what Aristotle says, any positive number is going to be too much. Because you can always build a ramp that contradicts Aristotle. And therefore what Aristotle said must be wrong. And there is no minimum force on that horizontal frictionless plane. And that is Galileo's argument. So he said, and you can write this down again in your notes, on a frictionless horizontal plane, a moving object is indifferent. He used the word in Italian for indifferent. The moving object is indifferent to being in a state of motion at constant velocity or at a state of rest. It doesn't really care. Yeah. Yeah. On a frictionless horizontal plane, an object is indifferent to being in motion or being at rest. In other words, that's like saying you don't need any push to get it moving. If it's moving, it'll stay moving. It doesn't care. It doesn't need any push force, like Aristotle said. And it's because Aristotle doesn't know his ramps. It's pretty simple. Now, this is the basic argument for this kind of idealized view of a system in which there's no friction. So that was Galileo's insight. And it's true that in real life, it's hard to get zero friction. But there are some things that are really close to zero friction. For instance, if you've ever played air hockey, an air hockey is a flat metal table with little holes in it through which they pump air, and so the air allows the hockey puck to stay up floating on a cushion of air, and it's almost frictionless. And there's various experiments that you can do with a hockey table of that kind. And there's other things that we can use to be frictionless. Another case where there's no air resistance is, for instance, outer space or on the surface of the moon. There's no atmosphere on the moon. Okay, anything that is, the exhaust fumes from all the Apollo rockets that landed on the moon are dissipated away very quickly, and so there's effectively no atmosphere on the moon. So there's no air friction, there's no air resistance on the moon. And now the space shuttle and the space station, they experience a measurable amount of friction. They're not totally outside 100% of the atmosphere. They got just a teeny bit up there, and their orbit will degrade slowly. That's pretty slow. It's mostly frictionless up there, no air resistance, but they can actually measure it up there. And and there's things that have lower orbits that have some resistance from the atmosphere. And every time you see the space shuttle land, it'll get really hot. In fact, the Challenger, not the Challenger, but the Columbia, when you guys were little shrimpy kids in 2002, when that re-entered and burned up on re-entry because of a damage to the wing, it was really, really hot from the atmospheric drag, but lower down in the atmosphere than where it normally orbits. But even up there, they can actually measure it. Now, we're going to now go into Sir Isaac Newton's laws of motion, because basically what we've got is Galileo's law of inertia. That's basically that's basically Newton's first law of motion. But before we do that, I want to go over a few ideas with you using your eye clicker. So go ahead and break that baby out. And as I've mentioned before, we're on frequency BB. Hold the power button down until the square flashes. Then type the letter B twice and you'll be on my frequency. And then my computer will be able to talk to your little device. Now, question 1 concerns the UCF shuttle bus. Raise your hand if you've ever ridden the UCF shuttle bus of any. All right, so that's a bunch of you. That's good. So everybody's been on that bus. And, those guys are maniacs. I'm not sure, but I think most of them, that's like a requirement to be hired, is that you can drive like a maniac, because They really jolt you around on that. Okay, here's your first question. You're riding the UCF shuttle bus, but it's crowded and you have to stand. Go ahead and vote. $30. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay. Yeah, correct answer is A. 87% of you got it. If a couple of you, 37 of you voted for frontward. No, and if you don't believe me, go on the bus. And no, I'm serious. I mean, when I say that they drive like maniacs, they take potholes and I don't know, but they always speed up to get going, so you're always going to see a forward acceleration no matter. And so if you next time you're on the bus, just stand there and then see which direction you have to brace. When he's going forward, you're going to tend to be, All right, next question. If you are moving at constant velocity, what I want to know is who took that picture. Oh, let me start the question. Yeah. Yeah, I know. I just started it. Okay. Who took that picture? That's what I want to know. God, that must be so fun, but I'd be afraid to actually jump out of the plane. But once you're out, it must be really fun. $30. Da 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 da. 15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right, let's see what you guys have. Whoa. Oh my goodness. We got some splaining to do. Look at that. We got a good distribution of concepts. So this tells me this allows me to gaze into your minds and see what you're thinking. And what you're thinking is a variety of different answers. And see, this is kind of a brain teaser because I have 2 yeses and 2 nos, and I have a yes and a no. And so if you want to answer yes, is it the right yes? Or if you want to answer no, which of those 2 no's is the right one? And you can see that a lot of people voted for D, but look at that, it's 42%, so that's less than a majority, right? That's what you call a plurality, but not a majority. And the next biggest one was yes and no. It depends on what direction your velocity is. Well, let's take a look at the correct answer. Let me move this out of the way here. There's your correct answer. And Galileo would have said, yeah, that's cool. If it's a frictionless plane, there's no gravity if it's on the plane. It's horizontal, and there's no friction. It's, so, but if there are forces, you can still get constant velocity. You just have to have a balance. Now, this picture is actually a good example. This is a picture of a skydiver. Now, whether he's at terminal velocity at the instant of this photo, I don't know. But raise your hand if you've ever done a skydive. Whoa. Did you raise your hand if you've been in a skydive and you hit terminal velocity? 1. Okay. 2, I see you in the back there. Good. It's pretty good, huh? Yeah. I said pretty good. Smarty Jones over here, exhilarating. But yeah, it's got to be cool. But terminal velocity, you always have downward gravity. And your acceleration downward is always 9.8 meters per second squared. But you have more and more air resistance. And the thing about air resistance is it gradually builds up in strength as you get faster and faster. So as you accelerate downward, you're getting faster. You're getting delta V, 9.8 meters per second for every second of free fall. But eventually your speed is built up to the point where you're getting so much upward air resistance, it completely balances downward gravity. And at that point, your forces balance and you no longer accelerate until you change the shape of your body. If you tuck into a ball or you get your feet first, you can get a little more acceleration. But then you'll come to a different terminal velocity. Now, another thing I want to point out about this one is option C right here. Let me see how many people voted for that. Hold on. 23 people voted for option C. That one you should scribble out because it is completely wrong. Forces are related to acceleration. And we're going to talk about that in Newton's laws of motion. So, students, I want you to bear something in mind with this problem. The correct answer is no, but you also have to have the right reason to say no. The worst answer is a no answer, option C, with a completely bogus reason for saying no. So just saying, true, false, yes or no, okay, that tells you something. But if you're really on the ball, you can tell me why. And that's the kind of situation that you want to be in. You want to be in a situation in which I ask you a question and then you give me your answer and I try to shake you off your answer. Like the DA in the courtroom, trying to shake the witness, And those guys in the courtroom, they really blast you with questions. But if you can't be shaken, if you know the truth, you can't be shaken with it. Okay? So, and I want you guys to be in a similar situation. All right. Baseball trajectory. We talked about this last time a little bit. And this one is, I believe, also in your textbook. This one is a trajectory for which the initial velocity, v subscript I, is 10 meters per second horizontally and 19.8 meters per second vertically. And so that would be this vector here. I just kind of made a vector 100 pixels wide and 198 pixels tall. And that's that arrow there. So that arrow is an accurate representation of the initial velocity. So kind of trace that in there if you can, with the tail of the arrow at the launch point on the left corner. And then, so let me just back it off here. So here's that vector. Okay, so there it is. And now, I'm going to ask you an IQ test question here concerning the landing point. And my question is going to be, okay, that's the final point on the trajectory. What is the value of the velocity going to be out here, the vertical component of the velocity? All right, so go ahead and make yourself a sketch. Try to make a nice sketch. And you will have this on the podcast, so you can go back and amend your sketch or make it redo it and make it nice and sharp. And have your clicker ready, because I'll give you this image back in a second. But first, I want you to tell you to hit the refresh key, because you're going to do a numeric answer. All right. So hit the refresh key, and let me start the question. Okay. Now you should have. What do you have? The number 1? Okay. You should start at 1. Okay. Good. All right. Now here's the question. Same diagram. What is the vertical component of the velocity Vf just before impact? Okay, so in other words, right at this point. And type in your answer to the nearest 0.1 meter per second of speed. And if your answer is negative 2.3 meters per second, type in negative 2.3. In other words, if it's downward, you can use a negative sign and type that in. And then hit the send key. All right, so go ahead and I see somebody pointing up to the screen with his part, and I see another guy pointing. I'm looking at you, and I'm trying to see if you're kibitzing with your neighbor, which I love to see. So definitely talk it over. If nobody's sitting next to you, you're on your own. But if you have somebody friendly sitting next to you, you're okay. Now, you can't do this on exam days, but in lecture, yes. See, I love this. I see somebody over here going like this. I see a guy in the back going like this. And just don't dislocate your shoulder when you're talking with your hands. It's good. Da 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 da. Da 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 da. Da 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 da. La na 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 na. La na 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 na. Na 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 na. Okay, 30 seconds. Make your decision. And don't forget to hit the send key. 15 seconds. Five seconds. 4, 3, 2, 1, 0. Come on, get your hiney in there. Get your answer in there. Come on, you slowpokes. Move it. I see there's 7 of you. There we go. Come on. All right. Come on. 4 more. Okay. You're not going to. I'm going to hit. When I hit the stop button. 298. All right. You had your chance. Let me see. But first, let me see what you guys have voted for. Okay, looks pretty good. The answer is negative 19.8. And now here's the breakdown of scores, and a good fraction of you did that. A couple of you blew it. You forgot your minus sign, and you need to have a minus sign. If you don't have a minus sign, if you have positive 19.8, that's the same as the initial velocity. And this thing, it's heading downhill. Over here, there's your vector. Go ahead and sketch that one in. And just for comparison, I'll copy the initial velocity vector over. Now watch this. Here it comes. All right, so there it is. They're vertical flip-flops. In other words, if you fold the paper, your notebook paper on a horizontal fold, they should cover each other up. All right? So those are your... And this is an example of something that I've mentioned before under the colloquial concept, the Lord giveth and the Lord taketh away. Okay? The Lord is take a thing away, or I should say gravity is take a thing away on the way up, but it's give a thing back all the way back down to here. So you get it all back, except now it's negative. It's downward. All right? These are symmetric cases, and just for, hold on a second, let me, so they're symmetric except for the flip-flop. And one more thing I want to point out to you. The velocity vector is always tangent to the path. And I made this really, really carefully, this image and then the vectors. And you can kind of see that they're just gracefully touching at that very last point. Now here's another example that I could ask you about. What's the velocity all the way up here at the top? Maybe, oh, no velocity up there? It stops. It just sits there. No, it doesn't just, I'll have to ask you that for homework. Now, I want to point out something. I was looking for a good image of a baseball, of a home run, arcing toward the outfield, and I found this on a sports website. This is a home run. Apparently, it's an epic shot out in Denver in 2013, Hunter Pence. And you can't really see it in this image, but if you look at it on the video, the baseball lands back here behind the bleachers. This is a concession stand back there. So they're selling hamburgers and hot dogs back here and dodging this guy's home run ball. But everything that this thing loses on the way up, okay, up here it's lost all its vertical component. It's getting all of it back until it slams in prematurely down here. So it doesn't get all the way back down to the same level. But if it did get to the same level, it'd have that same amount of velocity. All right, so neglecting the horizontal velocity, or excuse me, neglecting air resistance, the horizontal velocity is going to be constant. And the question I want you to think about now is, why is that? You know, how would you explain that? Why is it that the horizontal component of the velocity, you know, if it starts out at 20 meters per second toward the outfield, it stays 20 meters per second horizontally. If the Ferrari drives off the cliff at 20 meters per second, then all the way till it hits the bottom, it's still moving horizontally at 20 as well as vertically. But as long as it's moving, it's still got that 20 meters per second horizontally. Why is that? Now here's another picture. Here's the side view of Hunter Pence's home run. And actually, right up here is about where it hits the bleachers, or behind the bleachers up there. But anyways, theoretically, this is the curve that his baseball followed. Now, I'm going to ask you this question: why are the horizontal components unchanged? And I want you to answer it. And this is our first alphanumeric question uh, of substantive nature. So go ahead and, so this is not a Sharknado question. This is an actual physics question. You're going to be creating a sentence. All right, so do it carefully. All right. And hit your refresh key one more time. And use this code table to answer my question. Why do the horizontal velocity components not change, neglecting air resistance? Because if you do include air resistance, yeah, they're going to change a little bit. All right, so think of a good example. So notice there's no French fries in this. There's no Brittany. Leave Brittany alone. It's all straight concepts. Question in the back. Can I elaborate? No. I want you to elaborate. I want your I'm trying to gaze into your brain. This is my strategic method for doing so. So I'm serious. I want you to come up with the answer. So be creative. I hear clicks. I hear the sound of clicking. And talk it over with your neighbor. Let iron sharpen iron. Shark antennas are nowhere in this problem. Only regular concepts. Dude, what are you doing? Yeah. You let her type in her own answer. You did? Oh, okay. I know, I could see you guys comparing and stuff, but don't operate somebody else's clicker. You know what the most frequent answer? You know how many people have typed it in? 5. See, everybody's got a different answer. This is great. I love this. And everybody can have a correct answer. And they can all be different. The second most frequent answer is 3 people. Remember, an explanation is not the same thing as just repeating the claim. You have a claim, and then you have to explain why by not repeating the claim. And my claim is horizontal velocity components do not change. Okay, 1 minute. $15. Make sure you get your answers in. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right, let's see what you guys have got here. Okay. All right. Here are the results. And November Victor Zulu Quebec is the most frequent one. 13 people chose it. But you know what? That is wrong. That is wrong. And look at what they're trying to say. Horizontal velocity never changes. That's the same thing I said. That's not, don't laugh. I mean, I'm not saying that to make a funny point. I'm saying that to make a serious point. That is what you call circular logic. Now, moms are allowed to say that. Moms are allowed to tell you to go to bed. Why? Because I said so. You know, but in physics, circular logic like that is not kosher. So that one is not, that's an answer, but it's not a correct answer. That'd be a goose egg on a test. All right, now let's look at the next one. XZQC, X-ray, Zulu, Quebec, Charlie. The object never changes directions. That is also false. Okay? It does change its direction. At every instant on the arc of that baseball heading for the bleachers, every instant its direction is slightly different. Okay? Let's go down here. NSZQ, November, Sierra, Zulu, Quebec. Horizontal forces never change. Ooh. See, now that one is dubious. But it's not completely false. Because they're thinking about horizontal forces. But what's true, it's not that they never change. What's true about horizontal forces in this problem? Let's look for another NS, horizontal forces. We don't have it. What about NAPQ? Horizontal acceleration, not change. That is also tempting, but not correct. What is true about horizontal forces? What is true about horizontal accelerations? It's not that they're independent. What's true about these horizontal forces and horizontal accelerations? Yeah. There is none. Correct. They don't exist. That's the right. Now, somebody's probably got that. All right, and I'll be able to look at this in a spreadsheet and figure it out in short order. So great. Great, great, great. Thank you for participating in that question. Now, don't put your clickers away. We still got some stuff to tackle. Now, let's keep going. Oh, question.
So what was the wording supposed to be, or an approximate of what it was supposed to be?
What do you think? The student up here is asking me, what do you think the wording should be? What do you think?
I mean, there were a lot of words.
You mean back here? The answer? An approximate of the answer? That's an impossible question. There's a zillion true state. But now, if you want to ask how I would answer, let's see, how would I answer that one? Z N S, never horizontal force, or ZNA, never horizontal. Now, what's the colloquial? What's the Bugs Bunny sentence I used in class the other day? From the Bugs Bunny car. There's no such thing as horizontal gravity. Okay, that's the kind of thing that you'd see in a Bugs Bunny cartoon or a Roadrunner cartoon. You notice how in a Roadrunner cartoon, the coyote runs off the edge of the cliff, and he doesn't know it. He's out there at the edge of, out in space, and then he looks down, and then only then does he start falling straight down. But anyways, there's no such thing as horizontal gravity. That would be you can't make that with this code table, but that would be the concept that I mentioned in class the other day. So, but this, now what's your name again? Danielle. Danielle, the reason that I didn't give you an answer directly is because there are many correct answers. I will read all of the answers. I've got 500 answers I'm going to be reading sometime this weekend on a spreadsheet, and I'll be able to do it pretty quickly. But there's going to be a zillion of them correct. Question? I can't hear what you're in the third row. I still can't hear you. I just can't. 10 meters per second? For what? That's the 10 meters per second. That's the horizontal component of the velocity. It doesn't change. But that's not the explanation. That's the thing I'm asking you to explain. Why is it 10? In that example, why is it always 10, 10, 10, no matter when you look at it? And the answers were in, what I was discussing. So let's keep going. Newton's first law. Now, this is basically, we're going to be taking some notes now instead of clicking in questions. Newton's first law is basically due to Galileo, whom Sir Isaac Newton acknowledges as the master. So, Sir Isaac Newton took a humble attitude. He said, look, you may say that I've seen a far distance, but it's only because I've been able to stand on the shoulders of giants. And in other words, Galileo. Every object retains a state of rest or state of uniform straight line motion unless acted upon by an unbalanced force. All right. That's basically what Galileo said. If you're on that horizontal plane, you just keep cruising along it. You don't need any push force to keep you going at 20 meters per second or 10 meters per second or whatever this, the hypothetical velocity is horizontally, no force is needed. Unless you're acted on by an unbalanced force. Now this also includes the case of terminal velocity, because in that case, upward air resistance is balanced by downward gravity. So they're balanced, and you have constant velocity. Now, here's an example of balanced forces. The apple and the apple tree. Now, an apple and an apple tree has a pair of balanced forces. Okay, the stem, which is attached to the branch, pulls upward. Now, that stem has to have some tensile strength, some pull strength. All right? And it has to, because it has to pull up against downward gravity. So there's a weight force downward. Now, if the stem dries out and loses some of that elasticity so that it can't pull back, the stem breaks off. It weakens and the balance fails, and then the apple falls down. And if you're Sir Isaac Newton sitting underneath that apple tree, it falls on your top of your coconut, and you think about the law of universal gravitation. And that is supposedly the legend of one of the legends of Sir Isaac Newton. Anyway, this is a case of balanced forces and then the failure of balance. All right. Now, another way to look at this is in terms of the UCF shuttle bus. So let's go back to this picture. And let's just kind of encode the concepts in terms of what a bus is doing. Okay, so concept A, if the bus moves forward, you lurch backward. We talked about that at the beginning of class. I think that was our first clicker question. Now here's the other thing, and next time you're on the shuttle bus, just try it. And you don't actually have to stand in the aisle. You can feel this in the seat. If the bus turns right and you're standing out in the aisle, you're going to bump your left hip. Because it's going to be as if you're being forced to the left when the bus is going to the right. So when he turns the corner to go into the parking lot, you're going to feel, kind of a leftward bump. Okay, so if you are in the bus, you have to stabilize yourself. That's why they have all those little pull bars and stuff, the overhead bar and then the vertical ones. And some buses have those little straps. When I was a little kid, we rode on my dad would take us to work with him every once in a while in New York. He worked in the financial district down by Wall Street. And we would sometimes ride on the subway. And back in those days, they actually had leather straps. I was too tall. I was too small to grab up to him. But, you could see the adults on the bus, and that's nowadays they make them out of metal, but you have those what they call straps up there. And if you ever go up to New York City or someplace like that where they have subways, you can see that. It's kind of cool, but it's just like a bus. It's not that much different. Now, here's something that I want to emphasize, and that is that there's separate interactions. Okay, the forward-back can be different from the left and right. They can happen independently. It's possible that they can happen at the same time. So as you go into a turn to the left, you might feel a rightward bump on your hip, as well as if he's accelerating and getting faster as he goes through the turn, you'll also feel some backward pull. Or it'll feel like you're getting pulled backwards. Okay, so you can have both of these happening. And in a curved trajectory like this baseball, okay, you have separate components of motion. And the same thing with the first law in this context. You can have left and right, forward and back. And, I was talking to my son on the way to school today. I drop him off at school on my way up here to teach you guys. And I was showing him, what you can use to see accelerations in your car if you have one is if you have a hang tag on or anything hanging from your rear view mirror. Like if you have some fuzzy dice or you have a parking tag that's hanging there, something like that. If you turn right, the hang tag will swivel to the left. If you accelerate forward, the fuzzy dice will move backwards. So what happens if you have an unbalanced force? All right. Well, that's what we're going to talk about, because if you have an unbalanced force, just like this transformer, you're going to move. Okay. And so let's talk about Newton's second law, which tells us how things move. This is the middle of Sir Isaac Newton's laws of motion. What happens if you do have unbalanced forces? Well, what you do have is acceleration. This will generate for us our time evolution equations, our equations of motion. Sir Isaac Newton's second law is the simplest equation of motion for a simple object. All right, so what you do is you add up all the forces. Okay, and if anything does not balance, then you call that the net force. All right, so here's an example. Dwight Howard and LeBron James. Okay, so here's LeBron James pulling to the left, and here's Dwight Howard pulling to the right. Okay, so let's say that Dwight Howard has 100 generic units of force to the right, and that LeBron has 80 to the left, or a minus 80. To get the net force, you just add those two numbers. 100 plus a negative 80 is equal to positive 20. And so your net force is 20 generic units of force rightward. Now keep your clickers out, because we're going to do one more multiple choice question before we dismiss. All right, so Sir Isaac Newton says, all right, first thing you do is you figure out your net force. Okay, so if you're thinking Dwight Howard versus LeBron James, or a tug of war, one side maybe is going to be stronger. That's the direction of the net force. Okay. Then Sir Isaac Newton said, the more push force or pull, the more acceleration. And he said also, that should make sense. Arnold will get things moving faster than a little first grader, because Arnold's got, bigger muscles. Third concept in Newton's second law: the more kilograms of mass, the less acceleration. So if you're trying to move an aircraft carrier, or you're trying to move a rowboat, you're going to get less, and it's just you're going to get less acceleration from that aircraft carrier versus a rowboat, because a rowboat's got fewer kilograms. All right? Now, the way that he encoded this is in a mathematical formula. And that formula is this: the acceleration is equal to the quotient of the net force, whatever that works out to be, and divide that by the number of kilograms. F net divided by m. The kilograms are in the denominator, so the more of them that you have, Jacob, the less acceleration you're going to have. Okay, so if you have an aircraft carrier worth, 90,000 kilograms, or 90 million kilograms of aircraft carrier in the denominator, you're going to have a pretty small acceleration. But if you have 200 kilograms for a rowboat in the denominator, you're going to have a lot more acceleration. Same thing in the numerator, the net force. If you've got a lot of force from Arnold, or Chuck Norris in the numerator, you're going to get a lot of acceleration. Or think about it this way: if you have a really good car, like if you have, what kind of car has she got? Oh, Infiniti Q50. Fine. Nice. So if you have an Infiniti Q50, you're really fancy, you get some get up and go. But if you have like a beat, I'm not going to look at anybody, but I'm guessing that somebody in this classroom operates a beater, at least one. And if that's you, then you have a car that's, it doesn't have a lot of, get up and go. It takes 3 days to get up to 60 miles an hour. So that's why the F net is in the numerator. Now, if you go over to the engineering department and ask them for, what's Newton's second law? This is the way they'll write it, and it's a little more compact. F net equals MA, or F equals MA. And any, it's 1137. Any engineering student, they can be kind of annoying. Like they think they know everything and everything. And just anytime you want to tick one of them off, just look at them while they're doing their homework, and then just go, yeah, obviously F equals MA. And they'll say, how the heck did they figure that out? Because it'll always be right. F equals MA is always right. Anyway, so that's if you want to tick off the engineering department. F net equals MA. All right? Now, let's keep going. Item 6. Now, we know this. Acceleration is delta V over delta T. And the pull force or the push force is going to give you F net. And the acceleration depends on how much mass the object has. Now, we encode that with this set of equations. And really, F equals MA can be written in this manner here. M times delta V over delta T. And that last version is instructive for us because it tells you the things that you need to do in order to quantify force. If you want to quantify force, you have to know time. You have to have time measurements. You have to have mass measurements, and you have to have distance measurements, sufficient distance measurements, and time measurements and mass measurements to get a delta V, a delta T, and an M, a mass. All right? And that is why the force is called a derived unit. It is derived from basic distance, time, and mass measurements and then calculations. So you make a calculation of a velocity and an acceleration, and then you feed it in there. Now, here's another concept I want to share with you. Stopping time. If you look at this version, this third version, F equals M times delta V over delta T, you can think of it as stopping time. So if you have a stopping force, the more stopping force you have, the smaller the stopping time. And a good example of that is if you're in a car and you run into a brick wall, the brick wall is really rigid and the stopping time is really small. The brick wall has a lot of force to it and it wrecks up your car. But if you take the same car at the same speed and you plow into a snowdrift, if you're up north driving around on a snowy road, and I've done this, a lot of people, raise your hand if you've ever driven in snow. Hey, that's a fair number. If you drive in snow, you're liable to lose control of your car, but it's not too bad if you go into a snowdrift because the snowdrift slows you down gradually. All right? And here's another way to think about it. If you're doing box jumping over at the gym for your plyometric workout, what you want to do is bend your knees. Because if you don't bend your knees when you land, it's really hard on your knees shorter stopping time. We're not done. We got questions to do. Keep your notes going and we got several slides to go. We're not done. I've got 3 minutes to go. We're going to use every minute. So box jumping plyometric workouts, yeah, you got to bend your knees. Unless you don't need your knees 30 years from now. But most people, All right, hit your refresh key. Let's do one more Newton's Law calculation. And we're going to use F equals MA. We're going to do a real simple example of F equals MA. So hit refresh. We're going to be multiple choicing this one. And we're going to use a simple system. A kilogram of water and acceleration 1 meter per second squared. What's the size of your net pull force? All right, so let me start the question. All right. Oh. Okay, 30 seconds. We're not done yet, and you have a very important thing to add to your notes as soon as we're finished with this question. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, now apparently you guys saw the answers here. But yeah, it's pretty simple. And this is an important concept for us. Kilogram meter per second squared, that's known as the official metric unit of force. It is called the Newton. A force of 1 Newton accelerates a 1 kilogram object at the rate of 1 meter per second squared. And with that, you can actually you can calculate the weight force of an object. Because for weight, the acceleration is it's not 1, it's 9.8 meters per second squared. Now for homework, I'm going to ask you about Mr. T-Rex. And that'll be available by lunchtime tomorrow. If not sooner, you're dismissed. I'll see you next week. 11:45, right on time.